Recording is rolling. It is Thursday, October 27th. Today's going to be a lab day. Brett, before I hit this, a couple things. You guys know tomorrow is laptop day. So if there's anything you need to prepare for that, I don't know anything particular other than, as long as you turn in the one-to-one agreement. Okay. But I got look, you guys see this laptop cart here and all these chargers. Bring your ID tomorrow. That's what you should bring. Bring your ID. Because they're going to use a scanner and just like scan it in so that it'll pop real fast. If you forget your ID, it's just a slower process. You have to like type in your student number, stuff, right? So you guys can bring your IDs tomorrow for sure, right? Like student IDs, right? You should probably bring them anyway, but yeah. I got all these directions printed out, ready to go. Just going through the videos last night, and I think we are about ready for that. So that'll be tomorrow. One follow up from yesterday. Of course, there's a lot more energy stuff I want to tell you guys, but we're just push that off to next week. Leonardo was pointing out something to me yesterday. I was like, oh yeah, that's really right. This is like after the bell rang, you guys were walking out. Right? You guys remember these open systems, right? That involve like there were a couple of open systems, right? I wish I hadn't put this on the side. Right? Now it's really like a process. Like you start with this energy, you end up with this energy, and the differences. Here's what it looks like for the next one, which is like the car, right? Which we did correctly, right? Right. So this is for open systems. This energy you start with. Right, plus or minus the work change equals the energy, end up with subtracting because there's friction that's like slowing down the car. It's taking energy out of the system that includes only the car. Right, so similar process up here. I really should have. You could mathematically treat this as plus right here, but the better way to do it is to say minus friction force times length over here. So like force times distance. So I'm gonna type that over there. All right, so little thing, but that yeah. So all right, so that cleared up. To go into today's lab. So mechanical advantage. This is I'm gonna have you guys set up some pulley systems. Now I have a 5-to-1 mechanical advantage pulley system set up in the back. It's actually been a first day of school. Some of you guys may have gotten a close up look at that with some of the past labs we did. No, I'm just here. Thanks. Go crazy. Yeah. Okay, so this is how do you get mechanical advantage? But you guys heard like simple machines. Simple machines, you can get some kind of mechanical advantage. Now there are different categories of simple machines. You guys have ever used a lever for anything? Got leverage, right? Like say like there's a huge rock and you like put a shovel down, like move the shovel like a lever. Maybe like a seesaw sort of. A gear system, like an inclined plane, like the screw. Those are all categories of simple machines. And pulley systems. And you guys are going to set up some of these. Now, there's a way you can rig this up. You can wind the string around some pulleys so that you can get a mechanical advantage, which means you can lift something very heavy with a very tiny input force. Right? Actually, let's do this. I'm going to switch my screen over and show you guys parts of an animation here. Animation. Right, I'm just going to scroll through this just to save us a minute here. But there's like the story, there's Jack and Jill, these two kids that are trying to get water out of the well, but the bucket's way too heavy. Oh, she can't pick it up. He can't pick it up, right? The bucket's just too heavy. So like, what are you going to do? Right. So they try inclined plane, they try lever, right? The screw, that'd be like a giant screw right there. But none of those are helping out. Wait a minute. We could be like a pulley system. Right. So do you guys see a fixed pulley? You guys see the fact that axis is not moving, it's stuck in place. So that'd be called a fixed pulley, right? So great. So put the rope there and okay, well, that didn't help out very much because all it does is like change the direction of the force, but it doesn't actually give you any mechanical advantage. Or you could say mechanical advantage like 1-to-1, so it doesn't really help you. Okay? But what you can do is you make like a fancier system. Like what if you notice you like dove down at the bottom of the well? Let's make believe you can do that. It's a cartoon, right? Right, so do you guys see like a movable pulley? See the pulley is free to move up and down. See it's like free to move up and down, right? But do you guys see how, suppose the weight of the pulley, sorry, the weight of the bucket is like 100 newtons. Let's call it 100 newtons, right? Do you guys see like two ropes going up? And do you guys think the force splits like 50 newtons and 50 newtons, right? In fact, I had you guys do that spring skill lab a few weeks back. You did a similar setup and that was the case. That was true, right? Hey, do you think that therefore the tension she's pulling with is only 50 newtons? Oh, so she only has to pull with 50 newtons to lift 100 newtons. So she's like twice as strong. She's amplified her strength by a factor of 2. That's called a mechanical advantage of 2-to-1. Right? Guess that? Right. So now there is a catch though, which is that if she pulls the rope 2 meters, the bucket only moves up 1 meter. Right. So the bucket moves like half as fast as she's pulling it. Okay. All right. let's go towards the end here. Single fixed pulley, single movable pulley, right? The pulley can move, da, da, da. Right. And then now here near the end, they finally set up a 3-to-1 mechanical advantage. And you know it's 3-to-1 because we got a couple of fixed pulleys, yay. But look at this movable pulley. Do you see 1, 2, 3 ropes going up? Of course, there's only one continuous rope just wound around and around, right? But it's like this weight is being split 3 ways. So if the bucket weighs 100 newtons, do you think it's being split 33, 33, 33 newtons? And she's only pulling with about 33 newtons. So her strength is amplified by a factor of 3. Now, again, there's a catch. She's paying for this by pulling it 3 times the rope. So if she pulls 3 meters of rope, then the bucket only moves up like 1 meter. Okay. All right, you guys got that? And so with that, let's switch back over here. Right. And oh, I drew you guys. What's the mechanical advantage of one that I drew here for you guys? It is 3-to-1, right? Good. Okay, we've got a couple of fixed pulleys. Oh, I see a movable pulley, and I see 1, 2, 3. Right, so it's a single string, but it's one. So it's like the weight's going to be split 3 ways, right? Hey, do you think whatever the weight this is, suppose it's this guy. This guy, 1 kilogram weighs about how many newtons? 10 newtons. 10 newtons. What do you think would be a pretty good prediction for the force rating on the spring scale? Yeah, about 3.5 somewhere newtons. Because that would be like a third of this, wouldn't it? Right. All right, so here's the connection to conservation of energy, right? See, you can't create or destroy energy. You can't amplify the amount of work done, right? You can't do that, right? See, if you could, that'd be really nice because you could run the entire world's energy supply on 1 lump of coal and it would just work forever, but it doesn't work that way, right? So the work that you put in is equal to the work that you get out, which is energy in equals energy out, right? And work isn't work force times distance. I meant to put this line before this one, but force times distance in equals force times distance out, right? And the force in is read directly by the spring scale. And the length pull, do you think you could like put a meter stick or a roller up here and measure how many centimeters this moves, right? And then over here, the weight, right? Now remember, the number stamped on the lab weights are in grams, like masses in grams. Can you convert to kilograms, then multiply it by about 10 meters per second squared? So if it says 1 kilogram, 1,000 grams, you know that that's 10 newtons of force. You care about 10 newtons of force. Weight is in newtons, right? Can you guys do that? You can do that, right? Right. And then you can measure the distance that this moves up, right? The height change, right? Now I have centimeters here. You could do meters, but you have to be consistent. You could either do meters and meters or centimeters and centimeters, but as long as everything's the same, right? Right. Looks like you get some centijoules out of this if you wanted to calculate that. Right. Right. Then your ideal mechanical advantage is just the ratio of the distances moved, right? So if you do, right, how much rope do you pull compared to how high does this move? That should be like a 3-to-1 ratio, right? Like pretty well exactly. Right? Now, do you think possibly maybe if these springs aren't exactly vertical, or if there's some frictional losses, or whatever details, that maybe this spring scale rating is a little bit more than it should be? Like you said, it should be about 3.5 newtons, somewhere in there, right? About 3.33 newtons. Right? But then you try it out, and it's actually like 4 newtons. Would that be probably more realistic? Do you think? Right. So that is really to the actual mechanical advantage, which is the ratios of the forces, right? And then if you use this, you can use this to calculate efficiency. Like if you do actual compared to ideal mechanical advantage, it might be something like 90% efficient, something like that. Okay. Right, you guys get that? Right, so you guys have a lab page. I'm not going to have you guys do a full AP style right today, but here's what I am having you guys do. Okay, so the rest of the class, you guys get with your teammates, get your hands on Alta. I'm going to have you guys draw. Right, you got 1-to-1 mechanical advantage, 2-to-1 mechanical advantage, flip the paper over, 3-to-1, which I'm very helpful at giving here, right? And then the real challenge, 4-to-1. And of course, I already have a 5-to-1 rigged up back here if you want to look at the 5-to-1. Okay? So, like you can just take this picture and just copy this picture right here. Okay? Let me help you guys out here. Let's suppose you want to write a 1-to-1. Okay? So you guys got your ring stand. Got some rulers on your desk. Got a ring stand. Okay? There's it could be a single fixed pulley, a weight, wrap the string around. Okay, and draw the spring scale right here. Spring scale. Boom, done. 1-to-1. Okay. 2-to-1. Well, you saw that on the animation, so I'll help you guys out with that too. Okay. You guys remember seeing the single movable pulley was important for the 2-to-1? Okay. And there might be multiple ways to rig up some of these, so there's no like single.
Good morning, Hawk. We started the interruption. We are about to begin the SAT NCR testing for all students who need a concordant score. Teachers, please check your email and send those students to the gym at this time. It's a very important test for these students. Thank you so much for your support. Have a great day, Vera. Go Hawks.
So this could be a 2-to-1 right here, right? Maybe not the only way to do it. And the yeah, again, there might be multiple ways to rig some of these up. Here's a spring scale, right? So do you see like, right, like 2-to-1 mechanical advantage? This is going to be a movable pulley down here, right? The pulley itself is going to move up down. Right, you guys see that? Right. So there's a couple of pictures. Do you guys think you can make some measurements with the spring scales that are back there in newtons, and you can use a ruler or a meter stick that's also back there, right, and figure out these boxes? You guys think you can do that? Okay. So the weight used, the height change, that's like the output. The force reading and the length pull, that's like the input. Okay. And the ideal mechanical advantage. And then while you guys are doing this lab, I'm gonna leave this page up here so you guys can use this as a reference. Okay. All right, you guys good? All right, you guys got the rest of class to knock these out. Just turn this into the grade tray before you walk out today, and I will be walking around and help you guys out.